Awesome. And we already have our first question. Next slide, please. Dan, tell us who is on our bench today?
Matt Holland with Performance Pipe. He's a technical, and they're technical resources. So anytime you guys have any issues with your pipe in the industry, he's going to be one of the guys you reach out to. Him and Richard have similar roles in that technical background. Paul Brodsky will be joining us shortly. He's the manager of McElroy University. So any type of fusion questions you may have, even if they don't pertain to this webinar, Paul will be on today. So go ahead and feel free to ask. And then Chris Waite with Secor, branch manager based out of Gillette, Wyoming. And Chris is a guy that can do it all. So we have you covered across any aspect you guys might have questions on today.
Yeah, so that bench, so we have two simultaneous programs going, the main program and then all the questions going on. And we greatly appreciate using the Q&A function for all of your questions. So what we've done with this deck is we've organized it instead of by the 8 major methods or the 8 methods of polyethylene, we've organized it by how you use these methods. So if it's a new installation, think the 5 on the left. If it's a rehab, think the 3 on the right. The only exception to that is oftentimes open cut is also used as a rehab method where we leave it in place and put in a new line. Go ahead to the reverse slide. So please go back to Alan. So here we have, just as a matter of data, a data point for you, half of the polyethylene pipe projects that we come across are open cut, whether it's a rehab or a new install. Usually it's a new install, but that's what we see. And this is the best data we have on what % of projects go in by method. So we have some of that data. And if you're putting a program together for your team and you want to know what certain data is by method, reach out to Dan Landy, and Dan can share some of this data with you so you can present to your team what you think the state of the art is and where the data is. So with that, Dan Landy, I'm going to turn it over to you so you can share with our audience the various methods of HDPE pipe installation.
Hey, Dan, before we get going too much, that parallel track is in full effect here. Ronald's asked us a question about when you have an egress of water and loose soils from a previous utility installation in an 8-foot trench, if you can't isolate the water that's coming in, or the groundwater, what are some of the techniques to stabilize the bottom of the trench? There are dewatering pumps, obviously, that could put in the bottom of that trench. Sometimes it's very common to put in what's called a 57 stone by its class of what comes through the sieve to be able to stabilize that bottom. You'd have a lift of all of that to be able to make sure that the workers can access the pipe safely. And then you can also dewater the bottom of that lift in order to be able to remove that. If that's not ample enough, you can also stage dewatering around that trench down to 16 feet, and then that will remove the water itself. If your excavation is lower than 16 feet, then you'd have to have stage dewatering as we go through that. But thanks. Keep those questions running, guys, and Dan, I'm not going to stop you. Keep going.
Awesome. Yeah. So one note before I start running through these installation methods, if you guys are on this call today looking for really specific information on horizontal directional drill or open cut, this presentation isn't meant to be an exhaustive resource for that specific method. But if you are here today looking for really specific detail on pipe bursting, open cut, horizontal directional drill, we do have those webinars pre-recorded and up on our YouTube page. Either find our YouTube page on your own at pepipe.org or just go ahead and leave a comment in that survey and I can get that information over to you. So let's go ahead and get started on open cut, Alan. So the last slide was really interesting, where we showed the breakdown between open cut installations and compare them to the trenchless. The trenchless are obviously very sexy options. They can save you a lot of money, disruption. Everyone knows the full skewed benefits available, but open cut is still dominating the market. Whether you consider it a rehabilitation method or just a new installation is up to you. But open cut, very similar to how we've been putting pipe into the ground for hundreds of years. So some examples, these are your new construction projects where you're putting in major infrastructure, but we do want to also consider it at times as a rehabilitation method. But for this this mindset we're trying to get everybody in today, we're considering open cut as a new installation because there's really no feasibility of an existing conduit to work through these rehabilitation methods that we're going to get to in the second half. One of the great things about installing HDPE, very similar to your ductile irons, your PVC, other pipe types you're used to. The M55, which is the manual for HDPE, actually has the same open cut installation requirements as the M28 and M23. Go ahead, Alan. My favorite method is horizontal directional drill. The reason I say it's my favorite, I think it has the most difficult installations, and it kind of really showcases the flexibility and the installations that HDPE can accomplish. So one of the main design criteria that we do see people adopting HDD early on is they want to get really aggressive with that pipe entry and exit angle. There's really free software out there called Borate, available by the PI on their website. And you can come in, do a feasibility study, kind of see what that bore path of the geometry of your HDD is going to look like. If you want to go ahead and use that resource, it's a great option. Next slide, Alan. And this just we're going to walk you through the process really quickly. So the drilling machine itself would actually be on the left-hand side of this image. And on the right-hand side is where you'd be fusing up that pipe string. So the first thing they're going to do is they're going to bore a pilot hole. If you were going to be drilling maybe say a 24-inch pipe, you start with a 6 or 12-inch borehole. And next slide, Alan. Then what they do is they attach a reamer. So they're basically dragging it back and forth. And each pass they do in that borehole is meant to expand. So they're pumping drilling fluid in there, that bentonite, that clay solution, to keep the borehole from collapsing. But while they're doing that, they're doing a reamer back and forth to expand the borehole. And then ultimately, like I mentioned, that pipe is going to be on the right-hand side. So it's actually not being launched from the same side as the equipment, which can be a little bit confusing for new people taking a look at it. And the one last interesting thing I wanted to mention about HDD, it's the only method where you're actually launching the equipment at grade or at surface. I mean, you can lower it by putting it in the trench, but it's not necessary. You can drive that machine right up to the side of the road, drill right under the road if necessary. And this is what one of those big tools look like. They start making the distinction about 24 inches, differentiating between a mini and a maxi. Obviously, I put the maxi on because we all like to play with big toys, right? Above ground, probably the most difficult method for me to describe. We get the most questions, and I believe that is because we are now getting into installation methods where people don't have their mind primed. No one's used to designing ductile iron or PVC above ground, so we really start looking at all the possible failure situations. Really, no concerns for HDPE, indefinite outdoor service life with that infinite UV radiation. Our one concern, though, is going to be controlling the thermal effects, and you can do it in a few different ways. Let's show them what that looks like, Alan. So on the right-hand side, you can see they're just using jersey barriers on both sides. If it's going to be maybe a long-term bypass, maybe 6 to 9 months, we have seen people pour concrete on there, but it's not necessary. Those jersey barriers are going to keep it in place. You see those a lot in canals as well. You want to chime in here, Richard?
Yes, I do. Donna Nichols was asking, can you please repeat the name of the tool you referenced for HDD? And I'm assuming that's the drill tool, Donna.
Yeah, I stumbled through that. It's PPI Borate. If you just Google PPI Borate, it'll come up. You just have to accept one disclaimer, and then you'll be able to use it. And on that left-hand side is a bridge crossing. I'm not sure if we're going to get into bridge crossings today, but when you're evaluating going across a body of water, why go ahead and use that existing infrastructure. You don't have to drill. Those are becoming increasingly common as people are getting more familiar with HDPE. And these are just some more examples on the left. So I believe that's a temporary bypass job going to all the pump houses from, I believe, Alan, that was a job in Baltimore. Is that correct?
This is similar. This is just showing just how complicated temporary bypass for large diameter sewer or transmission mains can actually be. So high density polyethylene is one of the most common pipe material types to be used and reused for temporary bypass. And that's all above ground and protected by the group when they do that. And then if it is damaged during that installation, they can just cut that section out and refuse it. So that's why we show it, Dan.
Awesome. Thank you, Alan. Next slide, please. Marine installations, we're going to spend the least amount of time in there. The least common, but they're very interesting. If you were looking to tie in an island to a mainland, it's really expensive to put a water waste treatment plant on a small island. So these marine applications can be strung out across long bays, lakes, etc., to attach service connections or extend service out. Really valuable when the soil has no structure. What we're getting at there is HDD needs to have some type of friction to be able to drill against. And with those marshes, swamplands, bayous, there's no that the soil doesn't have enough friction to be able to drill, and then also to keep that pipe into place. You could anchor it, you could weight it. But yeah, we're thinking these long extensions that are quite difficult when we start thinking about these marine applications. And these are just some examples of them fusing pipe out in the lake and rivers and oceans and whatnot, using it as a staging area. It's kind of an interesting principle. We like to include it just to show the flexibility and the creativity that comes along with designing with polyethylene. Plowing, probably the most common method that you're going to see outside of municipal water. It's not super common for municipal water, but another installation method that really shows the flexibility of the pipe itself. Extremely common, especially in rural areas when they're plowing in conduits for telecommunications, electric, the whole 9 yards. I think it's the video, Alan, correct? Maybe it's the next one. Okay. Yeah, so the next one, this shows they're drilling in gas, oil. There's 4 different things: gas, electric, or a type of conduit, and then a caution tape. So when they're drilling, they know what's coming, and then a tracer wire. So 4 different things going into the ground at once. Once again, this is great for rural applications. This is a dumb technology, so it's not going to be sensing any other crossing utilities. So that's why we mentioned, well, with those rural applications, they pretty much know if there's existing utilities or not, and they can avoid them need be.
So it's just forcibly placing these pipes in the ground at those locations, and yes, a dumb technology would be a correct way to be able to say this is just putting it right in the ground. If there were other utilities in there, that would be problematic. Obviously, this is a gas main, and then also a buried fiber optic conduit or other kind of telecommunication conduit to go with it. So they're showing you that you could do multiple at the same time. So here you go, D.
Austin, do you want to cover pipe bursting, Alan, as our resident expert, right?
Sure. So with pipe bursting, 3 things are happening simultaneously. As you can see, we're fracturing that existing pipe. We are creating a temporary soil cavity surrounding that existing pipeline, and then we are pulling through a replacement pipeline at that time period. So there's 2 primary types. Those are pneumatic and static. Pneumatic only uses high-density polyethylene as that impact hammer inches along as it goes through. It's also more predominant than static pipe bursting in its use, specifically with gravity sewer systems. So here we're looking at static pipe bursting. The only thing that's different really here is how we're delivering the force. Those 3 things that occur simultaneously are happening at the same time, but we're using a hydraulic power pack above ground that pushes and operates a machine inside an excavation pit that pulls rods or a cable through, and then they're breaking the pipe at the same time as they're doing that. So here's a primary example of some cast iron pipe that's being burst. It's been exposed at a service connection or a lateral connection, or some other type of connection to appurtenances or what have you. And then that pipe itself is fractured by the expander head. The expander head is connected to the high density polyethylene pipe in that manner, and it's just really coming through, as you could see through this video. And here's the next one. Go ahead and cover slip lining, D.
Yeah, so the next 2 are going to be slip lining, compression fit. There's similar, slight difference being whether or not we're going to have an annular space between the hose pipe and the new carrier hip pipe. Could you play this video really quickly, Alan? The one thing I wanted to mention, the main concern when we're starting to look at slip lining and compression fit, the assessing that pipe, really finding out if there's misaligned joints, proving out that ID, making sure we don't have any oval areas where if we slip a new pipe in, it's going to get stuck, and we have to reduce the ID of the new carrier pipe because of that. So I know it can be difficult to go ahead and peg, especially if it's a non-redundant line, CCTVing it. I know 3D technologies and scanning are becoming popular, but this is definitely good information you guys want to go ahead and get early on in your project and your feasibility studies, so you have a good understanding and don't spend too much time working on a project that's not going to be able to be completed. Richard, was this your project? Was this a job you did?
Yes, it was. It was in Miami. It was just a little bit east of the airport. So there was a question earlier about how long you can do slip lining or what the length, maximum length is. And again, that depends on the host pipe as well and what kind of condition it's in. This is 54-inch diameter slip lining. There's a fairly small annular space that we attach to that, but we were doing about 1,000 feet at a time. And it depends on where we were going, because the connections, there were some connections and there was also some manholes that we were going into. And there was big trench boxes we were going into. But that kind of depicted the length of that slip line job. So, but yeah, this was in Miami, and we actually the line was so clean that we just, instead of using the hoe at the other end there, we just pushed it in with the forklift. So it worked out very, very well.
Awesome. Thanks, Richard. Very similar to compressive fit would be a compression fit. The difference here is we're actually going to temporarily reduce the OD of the pipe just long enough to be able to pull it in. So we're reducing the OD as it comes through that die. And then whenever we release the tension that they'd be pulling on this image from left to right, whenever that tension is released, the HDP is allowed to expand back to its initial pipe diameter. And what that leaves us with is no annular space. So when you're having issues and you really need to maximize your hydraulic flow, compression fit can be your best solution. Very similar to slip lining. Here they would be spraying. You can see the pipe's a little shiny on the right hand side, and then again coming to the left. They do spray oil as it goes through that die to reduce the friction. But other than that, there's really not a whole bunch of design concerns, as long as we really are confident about the ID of that existing hose pipe. And with both compression fit and slip lining, they can either be structural liners or just a liner itself. So it really gets back into the assessment of the original pipeline. And I know Alan plans on talking about the assessment a little bit here later on, so I don't want to dive too deep into it.
Semi-structural liner would be not a full structure from withstanding the pressure class and then working with the existing hose pipe. One of the important things that needs to be noted about compression fit that's different from slip lining in some ways is there's a whole lot of force that's generated by stretching that HDPE. That material has to go somewhere because it goes from a larger OD to a smaller OD temporarily. So you'll see a lot more shoring, a lot more backing on that soil die interface in order to be able to ensure that this process doesn't pull through forward into the soil column and then force itself into the existing pipe as we go through there. So as Dan showed, there is definitely when this pipe is allowed to relax, and in some instances, this relaxation can occur to 2 to 24 hours. We typically recommend that 24-hour time period. It pushes up against the ID of that existing pipeline, resulting in no annular space as we go through there. You do have to make sure that it's clean. We had a good question about what do we do with valves. In valves, those locations become excavations. So we just remove that valve, and if we have longer runs, we can pull through, or that valve location itself then becomes an entrance or an exit pit. This is similar to slip lining and pipe bursting, and the fact that we're not really going to be able to pull through those valves as we come through. So Dan's done a good job getting us quickly through those installation methods, because by the time that we get to the decision-making process and show you the case studies near the end, we want to make sure that you've seen the available options, seen what questions we need to ask through this whole thing, and then keep going all the way through to show why we selected those installation methods as we came through. And we're going to look at the application of the pipe. So that's what is its use. This is one of my favorite parts of getting to interact with all of you out there in the interweb here, in order to be able to look at how you're using pipe, how are you using HDP in the various processes that you use it for, and sharing those project details with us makes me really happy, because it's really cool that you can do that much stuff with different municipal applications. So we look at are you rehabbing it, or is it a new install? And as Pete mentioned earlier on, sometimes open cut can be used for just direct replacement of that existing pipeline, as well as maybe installing a new redundant line or something of that nature. We're looking at condition of that existing pipe. Is it necessary to be able to find that condition? In some instances, for pipe bursting, we don't necessarily need to have all that condition, as long as we can stick those quick lock rods through that pipe, attach on to the expander head, and break break that existing pipe will be happy, a happy camper. Type of fluid conveyed. These are all data collection points that as pipeline engineers, operators, contractors, and consultants that are on the call here, you're going to ask these questions anyway. What's that operating pressure? Is that going to drive the selection of the DR, or maybe the pull forces that this pipe experiences during construction? Is that going to drive that DR rating as we're looking at what kind of tension that pipe is under during a horizontal directional drill? Plan and profile, job site locations and conditions and project timeline. We wish project timeline wouldn't drive the selection of installation material or installation method, but sometimes it really does. And these are all the general complexities that you have to evaluate when you are designing your project. So in rehab, what are we looking at? Is a condition assessment necessary? And pressure pipeline has different implications for condition assessment than gravity sewer pipelines. And it's often very common to clean and CCTV inspect a gravity sewer at the same time, because that's what the manhole does, is provide us access to that line segment. In a pressurized pipeline, that pipeline is consistently under pressure, so we have to isolate it, dry it out, perform those, or they do have some live inspections in order to be able to make your way through that pressure pipeline under live condition as we go through. What material type is it? That's going to be one of the prime things that I ask, because we're going to know a whole lot about the installation time period, the age of the pipeline, whether or not that generation of pipeline itself is more likelihood of failing or not. And we know a lot about different pipe types to be able to predict maybe its remaining service life as we go through. Repairs are huge. And statistically speaking, the time period between the first and second repair on any segment of pipe can be as many as years, but by the time that we get to the same segment of pipe failing fifth and sixth time, that can be as little as a few months. What you don't want out there as an operator of a pipeline system is what we call a stainless steel pipe, in which case it's got repair clamp, as you're seeing here. Hey, Pete, yes.
Say repair clamp 3 times in a row. Hey, so with that bottom image, I love that image. You know, oftentimes we're asked, how do you pipe burst a line segment, Alan, when it's got that many repair clamps on it? We get this question a lot. How does that happen?
You don't, Pete. It just becomes an excavation in many instances, and that becomes your machine pit. Sometimes you can burst through a lower quality repair clamp, and sometimes it'll just drag it through as you go through. In water main failures, what is there a lot of? Water. So the question about dewatering earlier is definitely thinking in the right manner, in the right way as to how do we deal with that. And this picture is another example of sometimes the never-ending effort of being able to deal with some of the logistics behind it. So in new installs, just because we have tight corridors sometimes doesn't necessarily mean that you can't get in there and install the pipe that you're looking at. What you're looking here is a small horizontal directional drill. I will correct Dan earlier, that 16 inches is the differentiator between maxi and mini, and not 24. And sometimes it's the length of that drill as well. And the horizontal directional drill operators will have a lot of different machinery and even at their disposal for ownership or rental or what have you. But here we've lined up you could see a road curvature as we go through. And yes, it could be a challenging job site condition for limiting access, but they still can make it work. And a lot of places we get general questions about HDPE as people haven't thought through all the logistics. And then at the end of the day, once we do, guess what? You still can make it work, especially when we look at open cut. We're going to ask a lot of the same questions. And now with new installation, there's an additional design burden as to which we need to look at topographic features above ground. I always love to look up, as well as try to imagine what it looks like down below in the utility surveys as we go through, and existing soil conditions. Rehab for legacy conditions, there's a lot of corrosion, as you saw earlier, in heavy scraping of that metallic pipe before we did slip lining through this. They need to be cleaned. We need to be able to look for any repair clamps as we go through it. The ID of that pipe needs to be confirmed. That's an important part of selecting the replacement pipe. If we are slip lining or compressive fit slip lining, obviously we need to know what that ID really is. bell and spigot joints could have settled. It could be a problem to be able to slip line in there if there's a sunken pipe through there. Again, you guys are thinking, and gals are thinking through all of this stuff because we had a good question about settled joints and what have you. If we cannot repair or straighten that through pipe bursting, it becomes a point repair through it. And it's possible, obviously, in a slip line condition that you do that point repair in advance of the project through that as well. So some of the technology limitations are going to drive your installation method selection. There are some pipes that you can't burst. The pre-stressed concrete cylinder pipe, the cross section that you're seeing in the bottom right is a prime example of a heavily reinforced mixture of different elements that goes into creating a pipe. And I hate to target PCCP directly, but there's a generation of pipes in the 70s that stretch the material a bit. Statistically, the Water Research Foundation has looked at this, and that pipe in larger diameters has a higher likelihood of failure. And then when we get into big pipe, we have a higher casualty of that failure as it goes through. It's much more painful for a 48-inch pipe to burst and cause some above ground disturbance than it would be a 6-inch pipe to burst through that. HDD doesn't maintain a good constant slope very well. So it's not typically used to install gravity sewers as we look for a constant slope on that gravity sewer system. Friction forces during either horizontal directional drill, compression fit, slip lining, or pipe bursting may actually push you to a thicker DR rating. So Richard, come on and tell us about pressure real quick, and then the thicker DR rating. What does it mean to have a thicker DR?
Yeah, exactly. Our pressure rating is based on the heavier wall we have or lower DR number, the higher pressure rating we have. So it's based on our thickness. So it's the ability to hold hoop stress at the nominal wall thickness. And that's really what it's based on. So our DR 17s, 21s, 11s, 9s, 7.3s in the oil business is very typical to get up to that 300 PSI type number. So the thicker the pipe, the higher the pressure rating. But that also contributes to your installation aspects as well, because you can increase, because of the surface area increases of that thicker wall profile, you get some better tensile strengths to be able to pull that in longer distances as well.
Okay, great. And you'll see here in the bottom picture, of course, that's everybody's nightmare in a very dense city that's just built and built and built over time. There's very little trenchless that you could do in these applications to be able to come through and install it. So we just had a question from Randy about what types are suitable for pipe bursting. There's primarily a fracturable and a non-fracturable pipe. A fracturable pipe would be something that breaks fairly simply. A cast iron, vitrified clay pipe, asbestos cement pipe, a non-reinforced concrete pipe. You can cut through PVC pipe with a splitter, high density polyethylene pipe, or other pipes like that. The ones that we're not going to be able to burst are going to be a heavily reinforced concrete pipe, ball and socket ductile iron pipe, the pre-stressed concrete cylinder pipe that you see. The ones that are troublesome are going to be ductile iron, more younger generations of ductile iron, and then also corrugated metal pipe as we go through. So we do have a whole pipe bursting webinar in more detail for you under our YouTube channel, which a lot of people definitely take a look at. You can always shoot us a note to see if you got something special. So when we look at that plan and profile, now we're looking at the layout of the actual design. So we're looking to see what our service connections are, what our pertinences are from point A to point B, the valve spacing. Typically, what limits our trenchless technology installations, even though we are continuous pipe, we can get long runs. In a gravity sewer system, it's going to be the manhole to manhole spacing. We're typically not going to be able to burst through that manhole if it changes direction on the pipe run afterwards. If it's linear, you can burst through a manhole itself. In a potable water system, you're going to look at valve to valve spacing. We're not going to burst through that valve as we go through. So you're going to have to make those as an excavation as we go through. Yes, Richard.
Yeah, and everybody, just don't forget, like, especially in gravity systems, because we've had these experiences in the past, when you go manhole to manhole and you pull that pipe through that manhole, of course, we have all kinds of restrictions on infiltration and exfiltration of those manholes. We have to seal those up a little bit so that doesn't occur, but leave that pipe longer, because when you pull pipe, it extends and it elongates a little bit, or the surface temperature is a lot a lot warmer than the soil temperature, that you will get some contraction of that pipe. And we have seen it before where that they come back the next day, they've kind of semi-grouted it or sealed it, and that pipe is gone from the manhole because it's pull enough through, or they off just to save themselves some time. So don't forget about that aspect of expansion and contraction, because it does occur in polyethylene.
So, with that in mind, in the majority of situations as to which we're stretching this pipe, such as compressive fit lining, horizontal directional drill, those are temporary conditions. That's why Richard said you simply pull more. So we always want to measure twice, cut once, as the old adage said. But in trenchless application, they'll often add significant amount of HDPE on either side of it, so we don't pull through that. In a more permanent condition, such as above ground installations, then we're looking at some of the temperature fluctuations, and that's a little more complicated in the assumptions that you have to make about the install. And we'd be happy to work with you on some of those specific to above ground as we go through it. Yes.
So Alan, last week I posted an interview with a Garney associate who's a job superintendent who had an example last summer where the pipe shrunk 7 feet. He had figured, oh, it'll probably shrink 6 inches. It actually shrunk 7 feet. That was a long run, and it was a hot summer day.
That's a long run, Pete. Absolutely. So we've got a great question from John Jackson about pricing and in comparison between trench installation PVC versus pipe bursting with HDPE. Oh boy. It depends really on your area, where you're at, what's going on with the install, who the contractor is, and all sorts of different things. Regionally, it makes a big difference if there are more contractors familiar with the trenchless installation itself. There's a whole lot of contractors familiar with open cut. So they've got a better baseline as far as costs are concerned. Depending on the size of the program, the city of Houston is one of the largest consumers of HDPE for pipe bursting and gravity sewer, and they've gotten the cost down to $30 to $50 a linear foot, which is cheaper than cured in place pipe in that area. So that's a pretty good cost for pipe bursting. Yes, Pete.
So I'd say, depending on who asked the question, give us more detail on where your project is. We'll put you in touch with somebody to give you a good cost estimate. Generally, Alan, how I answer that question is absolutely. It depends on the region, depends on the market and how mature the contractors are. But before COVID, polyethylene was about 10% more expensive than PVC off the shelf. Now we're less expensive than PVC off the shelf. And with trenchless, 90% of all trenchless jobs are polyethylene. So trenchless is typically 40 to 60% the cost of open cut. But once again, projects vary. So it's a difficult question to answer with certainty.
That restoration cost is often a big one, and it's also a big burden on your residents and your customers, because especially in suburban environments and urban environments, when we have a lot of things above ground, established landscaping, trees, and things like that that people want to protect, that trenchless becomes much better use, but you're not always going to be able to low bid those social or environmental benefits. So new installations, that HDPE allowable bending radius is often way more forgiving than the installation requirements of the machinery used to do it. We are going to up the ante a bit on the engineering required for new installations. One of the things about trenchless using pipe bursting, slip lining, and compressive fit slip lining is the fact that you have a proven conduit location. So we know from A to B, we have a working pipe in that area, and it allows us to be able to minimize the amount of design that we're required to do on the front end. Not so for new installations, in which case contractually we're obligated to investigate the A to B path, whatever that might be, of that new installation, in which case we're going to look at soils, we're going to look at third-party utility conflicts to be free and clear of, clear bore path to make sure whatever obstruction we're going over or under needs to be clear clear from what we're actually doing with it, that project itself, and soil changes. We definitely want to know a lot more about the soils with regard to a horizontal directional drill, and as we get through. Being able to work around third-party utilities, as you can see in the bottom right, is a pretty big issue in very dense areas, in which case we spend a whole lot of time protecting those. So we'll spend a little bit of time with deeper installations. And now we get a lot of that question itself: segmental pipe and a 20-foot stick, 13-foot stick, 15-foot stick, whatever it might be. Sometimes it's easier to get that trench box that's more the length of that size to work with that segmental installation. Now the trench box, the hole, and any type of shoring that you go, even as we go deeper from what you're seeing here with the steel sheet pile, the deeper the installation, the more costly and more expensive that shoring becomes. But the width and the limitations for these shoring devices are often always there to keep the worker protected, more so than provide safe access around the pipe. Not safe, I mean embedment access, thank you, around that pipe itself. So we're keeping the workers safe in all of these aspects of it. When we get into seeing proficiency, productivity in a long continuous run pipe, if we can shore longer areas, make those excavations, fuse up that pipe run and put it in that deeper shoring, we're going to maximize our productivity as the actual excavations, and then the backfill and compaction as we go through that are often very timely efforts to be able to go through that. Obviously, MOT is going to be an issue in shutting down any type of roadway within a suburban or urban environment as we go through. So here's a poll for you. What percentage of your time, your projects are rehabilitation instead of new installation? You can go through and definitely answer that for us, and I'll keep going. But you can install high-density polyethylene, your contractor can, in many of the same manners as to which you'd install segmental pipe. And when we start thinking about productivity on the back end of it and the front end, we'll be able to get more shoring devices, get more areas, and be able to open up and get in there a lot quicker. Go ahead, Richard.
Yeah, one of the things that I saw in transition from segmented pipe or bell and spigot installations on even on open trench versus polyethylene segment, a lot of the inexperienced contractors, they would lay the pipe along that whole system like they would a bell and spigot system. Whereas for making the train for the polyethylene, you can do that in one location and then just pull that string into place to where it has to go, like that drill or that pull or that, even laying it down or lay it right across the top. You don't have to move the equipment. So that actually saves a lot of time.
Absolutely. One of the things that we show here is definitely in deep excavation, since we get technical logistical questions about it. But if you don't have that deep of an excavation and you can afford to be able to not have somebody in the trench, we now can take full advantage of that long continuously fused pipe as we go through and be able to maximize our productivity. We'll keep going. The job site location and conditions obviously is important. This is regional to wherever it is that you're working. We do run into lots of you out there in the consulting world that do work all over the country and in different locations as well. We answer any number of questions from Alaska to Canada to Hawaii to Florida that have unique things, and I'm always asking those questions of, and so is Dan as we go through. There are some handy things available for you for references. USGS has good soil conditions for you. That's typically the top portion of the soil column, and not something that's suitable for exploration for deeper depths as we go through there. Obviously, as competent design engineers, you want to be able to answer the depths of the soils when we get into complex drills or anything else that's complex installation as we go through. But these are simply that helps us understand the project locale. You can go through and find these in the references fairly quickly to come through. Those local soils should be suitable for native backfill if you are necessary. So there's a classification of soils for us. Class 1 is going to be the best compacted backfill that we can get into, all the way down to class 5, which will be the muck, the peat, the organic moss, those things that we don't want to use to surround any pipe as we go through. In some instances, depending upon what's on top of that pipe, you're not necessarily even going to have to compact that pipe all the way up to it. It does help. That's part of the soil stiffness factor that's associated with the installation. And then that DR rating that Richard, stay on Richard, mentioned earlier gives us a thicker pipe wall. That's the pipe stiffness factor. And those two things work together on the denominator. Our loading is on that numerator as we go through. Richard?
Yeah, and just we have to reiterate this quite a bit on the haunching and things like that, but that really locks that pipe in and really adds to the pipe stiffness. So you need to consider that backfill support, especially when you look at your H20 or H80 loads or whatever your dynamic loads are as well. And it may or may not change the DR that is applicable. So just always keep that in mind, that really adds a lot of support mechanism for the pipe. And you want to make sure that you're not over designing too much, which may also help your cost factor as well.
Alan, a couple things. Thank you, Richard. Couple things for our audience. This is a 75-minute webinar, as most of our webinars are. And Alan, we've just had 2 good questions on HDD. The first was, hey, what do I do if I have sharp-edged rocks?
Okay, so sharp-edged rock in that manner, something of that nature is typically going to be caught up during that reaming process as we're coming back through. It's that change in that soil condition that's going to plague that reamer as it goes through. So they have different reamer types for different varying soils conditions, which include rocks, cobbles, limestone, sandy soils, and other things. We want to know about that changed condition. We want to know, and that enlarging of that borehole that Dan had mentioned earlier, where it's about 50% larger than the actual pipe itself, is going to help ensure that we remove any type of negative material or not defunct necessarily, but dangerous material for the production pipe as we pull that through. Good
question. It also goes to the issue of we're allowed a 10% cut before we lose pressure, which is good to know. And the second question we have, what I think is from a city engineer, Alan, who's trying to give guidance to contractors in his community. How far down should he tell them to put their telecommunications conduit? As you know, telecommunications conduit's all polyethylene, right? And they're using that to bore under the municipal improvements. Is there a good rule of thumb versus distance below the lowest improvement that they should stay?
That's a great question, and it brings us to one of the things that's plagued the HDD industry for smaller diameter quite a bit, which is called a cross bore. So a lot of times you can bore through a gravity sewer pipeline or a storm sewer pipeline, and then put your new smaller conduit through that pipeline, and that's at that same elevation level as to which we're having that conflict. Unfortunately, there's not really a rule of thumb that I'm aware of, Pete. The underground world out there can be pretty fierce when they're trying to put pipe in a new location and avoid everybody else in different areas. Obviously, the elevation control, that inflow that we're looking at for the line of the gravity sewer and the line of the storm sewer, there's a limitation on depth that we can get to achieve for the lowest depth that a pump station can handle to move that back around. Pressure pipe doesn't have that issue, as it's always under pressure, so it'll be a little less deep than the gravity or the storm sewer, but still below the frost line. As far as conduit is concerned, for telecommunications, they're probably going to want to try to stay lower, or higher in depth, but really it's up to wherever they can find a good spot.
Thank you.
Okay, so we just have one more little quick bit on that job site location and conditions with regard to soil types. We put this table up here for you because it's an example of running calculations for complex installations for burial depths. Now, the majority of installations for burial depths, not to beat this horse a bit here, is just to most of your installations are in a design window of 2 feet for non-H20 loading or 3 feet for H20 loading down to 25 feet deep. And then any of those installations from a DR7 to DR21 in pipe rating, you don't have to calculate anything. But if you did want to calculate and go through those things, the Alliance does maintain spreadsheets for you. We can help you, guide you through that with your project specifics and turn you loose on those as well. This pipe material type and the flexibility that we observe can be pretty good for environmentally sensitive areas, as you're seeing here with some above ground installations in a area where we have forests and lots of elevation change. They wanted to not damage that forest. We're looking at seasonal considerations as well, sometimes that limit the window that we have for construction or limit the ability to access a pipeline and have things flow through it. Access restraints are huge. That MOT itself is definitely sometimes something that we have to have in the forefront of our mind more so, but it doesn't preclude us from using high density polyethylene or trenchless to do things more intelligently. We just have a bigger problem with maintenance of traffic to handle or access constraints through that. That's that public disruption as well. Sometimes the timeline schedule for trenchless projects are shortened fairly dramatically by being able to take advantage of the higher productivity, in which case we can take projects down from longer lengths of actual full bypass, full road shifts and traffic barriers down to simple outages from 7 p.m. to 5 a.m. at night. Put that road back together, let the traffic go through it, and then maintain exactly what we're preaching with this smaller schedule. So here's we're jumping right into the case studies. We are a little bit behind, so we are going to try to get through some of these. This panoramic hill project in East Bay Mud, a fairly complicated one, lots of 4-inch and 6-inch diameter to be replaced. One of the biggest things that was complicated about this was a lot of things. So there's a fault zone, so it definitely needed to be a seismic pipe within this area. Then the project itself had lots of switchbacks, so very tight conditions as to which they're trying to carry the pipe up to staging areas to do the replacement of the entire neighborhood, which is why you happen to be looking at a helicopter. All right. Helicopter. They're lifting that high density polyethylene up the side of the hillside of the mountain here. Well, in Florida, for me, I'm from Florida, that would be a mountain, but here it's just a hill. So they're lifting that all the way up, and then they're delivering that and working their way down as we go through. You could see just how difficult it is to maneuver around these switchbacks. East Bay Mud wanted to use high density polyethylene to push it through its paces to be able to test all of the allowable bending radius and confirm what the industry had said through this process, as you're seeing. And I will fast forward to the end of the story and say that they did confirm the table of allowable bending radius that the industry has pulled together for HDPE through this extremely complicated job as they moved through that and tested itself. So here's another one. Orange County Sanitation District wanted to do 14,000 linear feet of 36-inch force main to replace ductile iron and a different type of force main, a Techite force main. So here they used open cut in order to be able to install this. One of the first questions I would always ask through the discovery phase would be, is it redundant? If it's not, do you want the redundancy? That's a very important part of it. And then continue to go through. They chose a common trench for very long lengths of this force main to be able to get it installed. By choosing a common trench, now we're going, if you could see here, right down the middle of the road. Yes, it may be disruptive for everybody coming one way or the other, but we're going to be able to install both of these pipes in a trench that did not have to be accessed by construction crew to its fullest extent. And we did fuse that above ground in a laydown yard that was away from the project site and out of the MOT requirements, and pull that puppy right into place to be able to make sure that we took advantage of the very long laydown area and open trenches we pulled through it. So this was definitely a contractor familiar with installation of long continuous runs of pipe, their ability to be able to backfill around it, and use the pipe stiffness factor, as well as a high quality embedment material to be able to come through and make sure that they had adequate protection from any load above. So Richard, come on and talk to us about the Belgrave Water Pollution District as we're continuing to cruise through these.
Yeah, this was quite an interesting project. We put in 3,200 feet of 30-inch DR9. The reason we went with DR9 is just because of the drilling that we had to do to get back to the pump stations and also the treatment center. And what we had to do is, because in New York we had limited space to produce this long length to drill in, they actually did it all on barges. And there was a lot of challenges there, not only securing the fusion equipment or the T900 onto the barge to make sure it didn't get pulled off if resistance or winds came up with that string hanging out the back, but it worked out very, very well. The main purpose of doing this long string was because the area from the ocean side to the treatment center was that 3,200 feet was all marsh, and it was a protected, environmentally sensitive area. So we went right underneath it. And you can see in this picture here, there's that tube. Sorry, I just got the survey in my way here. There's you can go to the next slide, please. We had to lift it up. You can go to the next slide again. That's just another way to look at it. You can see the steel casing. So what we did there is the opening is actually the vent pit for the outfall vault. So we had to go backwards from the outfall vault. So then all we have is that steel casing in there, so we wouldn't get a lot of water piling into the vault, so they could still put the valves in place once we had that pipe drilled back to the treatment center. So it was a very, very successful installation. The hardest part, believe it or not, was just fusing the pipe together on the barges, because we did 200-foot sections, and then we joined the 200-foot sections to make the total length. And that was the biggest challenge, just because of safety, wind, all kinds of weather conditions that are out there that you're completely exposed. So that was the biggest challenge. Drilling it in was really, really good. Once we got to the end, we had to put in a little sweep that was, you can go to the next slide, Alan. Mm-hmm. And that sweep was manually built, or it was a fabricated fitting that was fused in, and we were able to connect those two lines and then make that whole system operational. So it was a very, very successful, and they were very, very pleased with how that whole installation went, because we didn't even touch a blade of grass in that swamp sensitive environmental area.
Just to summarize, this is one of my favorite examples, culminating the 8 installation materials that Dan talked about, the challenging questions that we always ask as to what exactly the project is, because this is a modification of a horizontal directional drill underneath an environmentally sensitive area that had no laydown yard, that used marine application to be able to stage, to be able to put your pipe into ground, correct?
Yeah, that's absolutely correct. And just to add chaos to mayhem, it was they wanted us to test every 4th joint, because we're out in the middle of the water. We have all these conditions, and that fusion equipment was exposed to a lot of different conditions, and so we had to physically break apart. So what we did, instead of chopping a section out of the lengths of pipe, we actually sent them 3-foot sections of the diameter of the pipe and the DR that we were using, so then they could test it in the fusion equipment so it wouldn't take away from any of those lengths. And then we would destroy those and produce the samples for pulling, tensile pulling and bending, to check those fusions and fusion conditions. And they all passed. It was a great success.
Awesome. Awesome. Pete and Dan were recently out in Arizona for rehabilitation of that PCCP pipe that I was talking about earlier. This one, the PCCP pipe was a 70s lifespan as it was put in at that time, abandoned in 2002. Then fast forward 20 years, they're starting to realize that, boom, hey, we can slip line this to be able to use that pipeline again and try to convey a little bit more flow through it. So in $17 million project, that 36,000 feet of 36-inch and 30-inch high-density polyethylene was able to provide an extra 10 million gallons a day of water to their area in order to be able to provide service. So that's roughly 100,000 people as they're going through to be able to provide this and then reuse an asset that otherwise they had abandoned from leakage and corrosion as they go through. My favorite part of this happens to be the installation video you'll see on the right, as to which case we're actually going around what would have been a couple of bends and fittings through this curvature on pre-stressed on the slip lining through it. We're pulling that through, reinforce the soil as it gets through there to allow us to make sure we get that HDPE curvature. There's nothing in this video that's going to hurt that pipe beyond its 10% allowable gouge ratio. And so what that means is 10% of that wall thickness can be gouged, and then you still have the full lifespan of the pipe. Pete had mentioned that a little bit earlier, but here you're seeing some great contracting ingenuity in order to be able to just continue this pull as we went through. They've over excavated to remove that bend or valve or whatever was in between. And now they're simply taking advantage of that viscoelastic behavior and allowable radius of the pipe to move it through. My favorite shot, of course, here is Dan. Certainly enjoying his time on site a little bit more than Pete, but who knows? They both had a great time getting that information for us out there and bringing you brand new images of great projects that are going around. Dan, you got something to add?
This is why I have trust issues. Never thought this was going to make an appearance in the webinar program.
Of course it was. So City of Miami Beach, we've talked about this one before, but this is one of the longest, largest directional drills to date. And one of the big things that was from our decision matrix, our decision making that we talked about earlier, this one originally was a micro tunnel. And as it come through and was bid, it was significantly more expensive, the tunes of $4 to $5 million for what they potentially could have saved via horizontal directional drill. The soils information was pushing it in that direction, and this contractor decided he was going to take out a little bit more risk to be able to try to get that installation in. Low pressure force main, another pre-stressed concrete cylinder force main as they go through it. Now they recognized the causation, or not causation, but catastrophe of failure in South Beach is it's the only pipe that's taking their sewage out to the treatment plant, the regional treatment plant. And if that pipe did in fact fail, you're not going to be able to shut down South Beach and tell everybody that they got to stop flushing their toilets in that manner. So here's some additional images. Very complex drill. A lot of our industry can do this. A lot of good folks that have talked to us and shared their stories with us, and also with you out there. Lots of good information once we do have that great project. I'd love to talk about it and get through it. But here's a little video clip to see a little bit through it. We're continuing to push the boundaries. That pre-stressed concrete cylinder pipe, slip lining, compression fit slip lining is going to continue to grow. One of the major reasons why is resin development is pushing us into larger diameter pipes at higher and thicker walls as we continue to move to install and push those boundaries. If there's an industry that likes to innovate, this is one of them. And you could see here just by the flyover as we're going to continue to look at it. One fusion joint in the middle. Took about an hour to be able to perform that fusion as we pushed down through it before they could start the process over again and continue to do that drill as we go through. Here's one that's near and dear to me. In Castleberry, when I ran the utility there, we did pipe burst 42 miles of asbestos cement pipe. That was a earlier question. It can be done in accordance with existing regulation. One of the complexity is the interpretation of those regulation varies widely across the country as enforcement of regulation is delegated down to the cities and or the counties and the areas of the states that are in fact doing it. So pipe bursting of AC pipe can be proven safe, and I've done quite a bit of work on that topic itself. You'll have to talk to me offline. Kiowa Special Utility District is another one in Texas that we, as the Alliance, have started from initial conception to the end, the actual project goal. From the first question of, can you burst AC pipe? Well, yes, you can. Here's this seminar. Here's this roadshow. Here's this information. All of that in here. Go forth and burst pipe, and they did so. We're very happy to see everyone out there advancing their infrastructure needs, which makes us smile and happy. It's Fort Lauderdale 7-mile force main project. This is a complexity of different installation methods. Again, project short timeline. They have all of this raw sewage material being able to pour into the water body that's there. One of the big things that caught my attention with this is every single day there were 20 to 25 vac trucks that were going from the upstream side of the force main down to the downstream side of the force main on a 24-hour rotation. When we start to look at that price tag, it's going to certainly drive way more than the actual cost of the program itself. But that was a fairly good job, big job, $65 million. 18-month construction schedule as it goes through there. Of course, they had other interesting challenges such as hurricanes and other things that required the construction crew to move off site and try to continue the process. With trenchless, we like to say, once you start, continue and finish. Unfortunately, with hurricanes and your forced evacuation, you're not going to be having to do that as much there. So HDPE came very useful in this process. Did temporary bypass in certain areas, definitely did compression fit slip lining, multiple crossings. So I say multiple, and I'm not kidding. 17 crossings through downtown Fort Lauderdale, which now has that above ground issue, the MOT issue that we talked about, the third party utility issue that we talked about, change in soil structure as we go through. So in many places, as we look in dense urban areas where we've built and rebuilt, and then we've also dug canals and installed things, we're going to look for steel sheet pile that may very well hold the foundation of the bridge in that canal crossing. Those are some of the things that we want to ask that question of in data collection. So I hope you're still with me. We got a lot of them. Not many have left from the top of the hour. That's why logistically we went through what can you do? Why would we ask all these questions? Tell us about your installation project. And then here's examples of how we took that stuff and really ran with it to find the benefit of high density polyethylene trenchless technologies and installed all of these projects. This one I always love because behind the scenes, we don't always, as design engineers, focused on just pipe installation or pipe rehabilitation. The top two things we're talking about, new installation or rehab, we don't always look at temporary bypass. And then in very large diameter, long lengths, the temporary bypass can be sometimes far more complicated than the actual rehabilitation of what we're looking at to begin with. So entering in those people behind the scenes, Sunbelt Rentals, Rain for Rent, all of these crew that maintain and own thousands of miles of high density polyethylene that continue to be reused and reused, cut, fused, refused, and then dragged all over the place to be able to provide the temporary bypass. We were working with Sunbelt on our above ground webinar a couple of years ago. And this happened to show us an exact case study of a highly complicated project where we looked at safe handling. We looked at how to move the pipe about, how to fuse it, how to connect it to a flange, which some of you have asked about, whether or not that's a good way to connect to a non-high density polyethylene system. So here, this one is only rehabbing 4,700 linear feet, but it's big, 78-inch combined sewer. So now we have to predict how much goes through the sewer, which we have good numbers on, but then how much it could rain, which we don't necessarily have good numbers on. 45,000 linear feet of 24-inch HDPE, ran through this, and then to get that together, to get the project going, took a lot of work to really make it all happen. I love to show this video and talk through it. Richard, I'm not sure if you've got anything you wanted to add, or Pete, we're nearing our 75 minutes as we come through. We've got a couple of more slides on resources as we go through, but here you could see everything in above ground the way that we want to see it handled. We want to see it fused. We want to see it manipulated.
Yeah, Alan, it's, you know, the challenges that we faced, you know, in very difficult situations, that we've overcome, you know, a lot of them, some of them, even the manhole situations, especially in petrochemical plants, are very difficult, high important type, valving systems, or whatever the case may be. I mean, it seems like we've stepped up and been able to design these things. So if you can't find access to the information you're looking for, you know, contact one of us, and again, ask those questions. We can usually find out somebody that has done something like these multi-valve prefab systems for temporary bypasses, or whatever the case may be. It could be an S-turn sweep through a city corner that you just can't excavate because of new installation of buildings, etc. So don't be afraid to challenge us, because we've usually come to the rescue in some cases. Don't know a lot of situations that we haven't been able to provide a design for you to alleviate your problem.
Hey, Alan, we have a couple minutes left, and I know you put some slides on at the end. I would love it if you'd take a minute and a half or so to tell us about the resources that are available to people if they want to work on a project. Thank you very much.
Absolutely. Dan, come on too, so you could talk about it some too. Pete mentioned screenshotting. This is a slide that you can screenshot with all the contacts from everybody here today. There's a survey at the end if you want your PDH. That is absolutely the best and easiest way to be able to get your PDH as quickly as we possibly can process that. So with close to 400 people on here today, we have a lot of information to process, but that's part of what we do, and we just want to try to make it as easier as we can. So I'm going to scroll through this. Dan, can you tell us a little bit about what you've done as part of the engineering program, and what people like Richard and Chris Waite and Matt Hahn do for us as part of that program as well?
Yes. So my main takeaway from today, reading through the questions and comments, is, you know, this is an ongoing conversation when you guys are designing these projects, and guys like Richard and Matt Hahn, obviously Alan and I all the time. You know, Alan, with your civil engineering background, we can really actually help people make these decisions and evaluate this job by job basis, until people are more comfortable using polyethylene and might not want to include us as much moving forward. But the resources, we have a master follow-up email with all the technical resources, all the details, all the handbooks, etc. So if you send me an email or just ask for the follow-up, all the follow-up information in the final survey, I'll go ahead and get that sent out to you. It's a Dropbox link that now includes our engineers package and all the technical resources that are free and available to the industry.
So the programs in its multiple years here, we have available engineers to be able to interface with you, not just Richard and Matt and Chris, but Dan and myself and others, to be able to make sure that we guide you through whatever detailed technical questions that you have for whatever your installation method is, and also case studies available to you. So it's never fun to be the first one to do it, but we've got lots of people, as Richard mentioned, that have done it before. And the logistics of thinking through the installation sometimes is hard to get to. So the simple fact that you've had well over 55 good questions talking about that logistics makes me really happy, because you guys are thinking through all, and gals, thinking through all of the things that we're really needing to go through. Got any last words for us, Pete?
Yeah, good job, Alan. Great job, team. Thank you, Richard Kolasa. Thank you, Alan Ambler, and also the bench, Matt Hahn, Paul Brodsky, and Chris Waite from Secor. Matt from Performance Pipe, and Chris from Secor, Paul Brodsky from McElroy. Great job. And Dan, just to confirm, if they want the PDH, they have to stay on after we say goodbye, and they can fill out that form.
Yes, please. We're going to hang up here in a second, and the browser should pop up a next survey. Fill out your contact info, and we'll get that sent out to you.
Great. Great job. Okay, don't remember what's next. We'd love to see you on the next webinar. Thank you so much for sitting through 75 minutes of our favorite topic. Bye-bye for now.